All right, so now we're going to move into Chapter 8. Chapter 8 is very weighty in terms of its concepts, but not very weighty in terms of its eventual problems. So we're going to have to kind of put our thinking caps on and kind of imagine some scenarios and see how things are going to change. So let me see if I can describe it. So suppose the average score for all SAT test takers, the SAT being an exam that you take in the US to get into college in many states. So tens and tens of thousands of people. The average is 1,000 and with a standard deviation of 200. So looking at individual people, at every single individual person that took the test to describe the distribution of values. Okay. So I put down here the shape. I mean, when it says describe the distribution, it wants to know three things: shape, center, spread. So the shape, well, we don't really know the shape. It could be skewed left, it could be skewed right. It could be uniform. It could be every single point value is just as likely as any other. However, that's mostly unlikely. It's probably normal. Matter of fact, I'm sure it's normal because they write the test so that it's normal. Most questions are kind of mid-level questions. Some questions are really easy. Some questions are really hard, but they expect most people to get in the middle, right? But we don't know for sure. Okay. Now the center is 1,000 because they said that the mean for all the test takers was 1,000. So the center is going to be 1,000. And then the spread is going to be 200 because that's what they said the standard deviation was. All right. Now, bear with me if you will. So imagine that you're in a building full of people, like a big, I don't know, school building, full of classrooms, and everybody's taking the SAT. Okay. So every room, just for the sake of it, we'll just say every single room has 30 people in it. 30 people taking the test in every single classroom in a school building. Okay, so can you imagine it? Kind of get it in your head. And we're going to look at the scores from room to room. We're not going to look at individual people in any one room. I don't go in a classroom and say, what did this person get? What did this person get? What did this person get? I walk the hall, and all that happens is somebody comes out and tells me what the average for that room was, and then goes back in. And then I go to the next room, and they tell me what the average for that room was, and so on. Okay, so I'm going to look at X bar for each room, not X, not the individuals, but X bar, the average. Sorry, that was bothering me that was superscript or subscript. There you go. So we're going to look at X bar for each of them. Every class is size 30. How is that going to be different from looking at individuals? So this is looking at X values up here. So looking at X, right? So looking at individual scores. But down here, I don't ever go into the rooms and see, right? I don't see the individual X's. I just know that the average from the room because somebody comes out and tells me. That's all I know. Okay? Now, what would we expect to have happen? How would those be shaped? Well, first of all, they should be normal, right? So what's going to happen is that you're going to well, let me tell you the center. The center is 1,000. We'll talk about the standard deviation in a second. But the center is 1,000. Okay, see, what happens is if it was 1,000 for individuals, then of course, shouldn't it be 1,000 for the X bars as well? See, if you go into any one room, you get people on the high end, people on the low end, right? And they balance each other out. And that room should be close to 1,000. And most rooms should be right around there. Very few rooms would be extremely high or extremely low, right? They're all going to be clumped around 1,000. And they're also going to be normal. Even if it was skewed originally, even if it was skewed left or skewed right or something like that. Like you can imagine skewed left might be possible for an exam like this, or because most people that would score low wouldn't take it or something like that. Or skewed right. Most people are on the low end, but just a few people are on the high end. You could imagine that. But what's going to happen is that if you look at the room's averages overall, they're going to balance out. And that means you're going to have most classrooms, most averages are going to be right around that 1,000. And less and less and less and less as you move away from the 1,000, right? Now I'm describing something else there too, because the spread is different. See, when you look at individual people, it's like, a single person getting 1,200, no big deal, right? That's just a standard deviation high, right? But having a room of 30 people have an average of 1,200. Think about that for a second. That means you have to have well, half of them roughly above 1200 and half of them below 1200, and they've got to balance out. That would be an amazingly high classroom. Lots of people in the 1300s and 1400s. That's high numbers for that test, right? So that's far less likely than an individual. Getting a single person to be 1200, it happens. But getting a room of 30 people to average out to 1200, that's not likely at all. Now, why? Well, because the spread is changing. The spread for individual people, look, individual people, some are high, some are low, right? You get a lot of variation because you're individuals. Hell, it wouldn't even be crazy to get a 1300. That's only 1.5 standard deviations high. But to have a group of 30 people balance out to 1300, that's unheard of. It's so rare, right? By the same token, what about 800? I mean, 800 on the low end, right? That's only 1 standard deviation low. That's not too bad for a single person. But for a group of 30 to average to 800, it means you had to have half the people be lower than 800. That's just really crazy low, right? Okay, so what we're seeing here is the spread is changing. The spread for individuals is 200, right? Couple hundred points, give or take, which means if it was normal, we'd figure a couple standard deviations, so maybe like 600 to 1400, somewhere in there, right? 400 above and 400 below. But when we look at it for the rooms rather than for the individuals, balancing out, take those X bars, that person that comes out to the hallway. I don't expect the people that come to the hallway as I walk it from room to room to be that far apart from each other. I certainly don't expect them to be 200 give or take from each other, right? Okay, so it's changing. Now, what's it changing by? And the answer is it's got this formula. You take the 200 and you divide it by the square root of n. N being the size of people in the room, or the sample size, number of people in the room, which in our case was 30. And that means that this shrinks to 36.5. Use a calculator, use Excel, whatever, right? Just type it. You'll find it's around 36.5. Technically, it's squiggly equals because I'm rounding here. Okay? Okay. So what's happening is it's getting packed in tighter. Room averages just do not vary nearly as much as the individual people within the room. Right? Think about it. See if it makes sense, right? Because this is the big heavy concept. This is the deal with chapter 8. And upon this, we're going to build everything from chapter 9 on, because we're going to work with nothing but samples. In the end, in statistics, it doesn't really matter that much what a single person does, right? What matters is how did the collective work? How does that average work for the group? How does the proportion work for the group? That's what matters to us. Okay. So, by the way, just on a side note, so suppose the individuals, see that purple, see that guy? That's the individual distribution. It's all, it's a little skewed right, it's kind of lumpy, blah, right? And notice the center is 1,000, right? And it's 1,000 for the purple one too, But when you look at groups of size 30, then the distribution makes this normal curve. Most of the classrooms are going to be right around 1,000. Very few are going to be way up high or way down low. Right? That's the central limit theorem in a nutshell. Central limit theorem says that as you take samples instead of individuals, as you look at the group's average, it's going to become normal, right? Normally distributed. It's going to have the same center, but the spread is going to significantly shrink. And it's going to shrink based on how big your sample is. So for example, suppose it was rooms of size 100 instead. So just imagine that. Like cafeteria is like a room full of, a building full of nothing but cafeteria size rooms with 100 people taking the test at any one time. Sort of like, the OWLs in Harry Potter, right? So if that's the case, it's going to be even less spread, right? Because there's even more people to balance each other out in that room. And instead of 200 over the square root of 30, it'd be 200 over the square root of 100, which would make this even smaller. You follow? So that's what we're doing in chapter 8. We're saying, okay, forget about the individuals. How does the group work as a collective? All right. And then how is that going to affect our probabilities, which is our next questions that we'll answer ourselves. So first, let's talk about the normal shape just a little bit more. So the sampling distribution of X bar, when we look at the averages, it will be approximately normal as the sample size n increases. Now, here's the deal with that. If the original data was normal, if it made this normal curve to begin with, right? If they say somewhere, this is normally distributed, something like that. So if they say those words somewhere, then the sampling distribution of x bar will be normal no matter what, regardless of how large n is. I could take n equals 2 and it would still be normal, right? Because it was normal for any, let me put it this way. The original distribution is n equals 1, right? So if it's normal when n is equal to 1, then it's going to be normal for 2, 3, 4, 5, 6, whatever. And the only deal is that the bigger your sample is, the narrower it spreads. See, n equals 30 makes it pack in really tight, right? Really tight, and then it has a higher peak, if you will, than when n is equal to 5. Good? All right, if the original distribution was not normal, let's suppose it was something just awful, right? So it made this kind of shape, like a box. That's a uniform distribution, right? Or whatever the heck this is, right? It looks like an absolute value distribution. And then exponential, whatever. I mean, whatever yucky thing it was. So those are the original ones for n equals 1 up here. There we go. I just wanted to kind of make a note right here. All right, so if n equals 1 are these ones, then how does it look when n is 2? When n is 5. See? So when n is 2, this one turns into a triangle. You learned that in grad school, if you go, right? And it's kind of forming some other stuff. And then, hey, look, by the time you reach n equals 30, they're mostly forming normal curves. Now, we're fudging that a little bit, and if you go on to higher level stats, you'll find out there are ways around it. Sometimes you need bigger than 30, sometimes 2 is enough, whatever. But for our class, we're going to say n is equal to 30. So we're saying, look, if the original data is not normal, then the distribution is normal as long as n is bigger than 30. Okay? All right, so if it was normal to begin with, then it's normal no matter what. N is 2, n is 5, whatever. If it's not normal to begin with, then we need the n is equal to 30. Now, one other thing real quick. This is all about means, right? So this is only going to work, this whole n is equal to 30 thing or more is only going to work when we're talking about x bars, like the average test score from room to room, that kind of thing. Okay. There's another thing we're going to do in 8.2 that's not this, right? And it won't be 30. 30 won't be nearly enough. Okay, but for when we're talking about the distribution of sample means, how do our x bars vary from room to room to room? How are they spread? What's their center, etc.? That will be normal as long as n is bigger than 30. And then it'll have a mean mu and a standard deviation. There's that formula, sigma over the square root of n, which is called the standard error of the mean, or standard error a lot of the time. Okay, so if you see standard error, all it is the standard deviation of the sampling distribution rather than the individuals. Right? And again, the bigger the n, the smaller this is going to be. And as long as n is greater than 30, it will be normal. Right? That's the central, the central limit theorem. But again, all of this is the central limit theorem, if you will, for population means and sample means. This is not how proportions are going to work, which we'll learn in 8.2. Okay, let's stop there, and I'll see you back here for example 1.